Today video lecture series. In this topic, I will discuss about an extended surface analysis using finite difference method in heat transfer. So, in this subject, first of all, we know about what is extended surfaces analysis of a finite difference method. The analysis of heat conduction and extended surfaces using finite difference method is a numerical approach to solve the heat conduction equation. In extended surfaces, heat is conducted through the material and also convected to the surrounding environment. And the scenario can be modeled by a 1D or 2D heat conduction equation, depending on the complexity of a surface. And the governing equation for heat conduction on extended surfaces, the heat conduction equation for a fin is often simplified to the 1D steady state form, considering uniform cross-sectional R and heat conduction in the x directions only. This is the graphic equations method of extended surface analysis in finite difference method. Is d by dx of a Ka dt by dx minus hp d minus t infinity is equal to 0, where T of x is equal to temperature distribution along the fin, K is equal to thermal conductivity of the material, A equal to cross-sectional area, P is equal to perimeter of the fin, H is the convective heat transfer coefficient, and T infinity is ambient temperature. For simplification, the governing equation can often to be reduced d squared d by dx squared minus m squared dt by d infinity equal to 0, where m perimeter m squared is equal to hp by Ka, where h is the local heat transfer coefficient, p is in a perimeter, and k is equal to thermal conductivity, and a is in the area of the particular plate. And extended surfaces analysis using finite difference method is used to solve this equation numerically. The FDM can be used in the FDM approach. The continuous domain is discretized into small nodes or points, and the second order differential terms are approximating using finite different approximations. And for instance, the second derivative d squared by dx squared at node is I is approximated as an d squared by dx squared is equal to ti plus 1 minus 2 ti plus ti minus 1 and delta x squared. Here is the delta x is the spacing between the nodes, and the steps for the FDM solution is in divided the fin into small segments of all equal length del x with nodes at each segment boundary, and set boundary conditions, and these can be at the base of x0, and the temperature is typically known as T0. We take an addition at TB. At the tip, x of L is the limiting in depending on the fin type. There could be different boundary condition. Example, insulated tip dt by dx is equal to 0 or convective boundary condition. And set up the difference equation for each internal node. Replace the continuous differential equation with their finite difference counterparts. And to solve the system equation, this leads a system algebraic equation that can be solved using methods like Gauss elimination and the iterations method like etc. And the conclude of this summary of these heat transfer numerical methods is, and also I will summarize about the heat transfer numerical methods problem we can find or we can estimate about the one-dimensional or two-dimensional fin element method. And also we can solve the lot of differential condition problems, including with the considering the boundary layer concept, and simplifying the equation can be reduced to d squared by dx squared and m squared t minus t infinity is equal to 0, and where m squared is equal to hp by ka. And in this problem, we also we need to discuss about finding the solutions of the perimeter length. And for another additional extended surface, we can estimate or we can extract this equation with these differential conditions mode into small segments. We categorize these small segments into a different type of part section with the base and the tip and mid of the exponential equation. And finally, we set up the difference equation for different mode conditions. And after that, we solve the systematic equation into the numerical methods like different type of numerical methods, Gauss elimination, Gauss iteration, something like etc. This is the video session about the extended surface analysis of using a finite difference method. Thank you.